network flow. And as I mentioned last time, network flow is one of the really elegant topics in algorithm design, and also very useful, both algorithmically and mathematically. We'll see today one of the mathematical consequences of this kind of algorithmic thinking. And I'm just going to write up briefly what the algorithm is again, slightly differently than last time, because last time we had an initiation phase where we actually produced a first flow. And I mentioned then that really you could just have thought of the first flow as being the flow of 0, and then look at the details for the residual flows and everything would work out. But it was more intuitive to start out with some actual flow. But now that you've seen a little bit of it, we should be able to start with just the 0 flow, or Fe equals 0 for all edges E. And then we have the residual graph phase build the residual graph GF from F. And the rules, remember, were for E contained in E equals UV, and F of E greater than 0. So this is an original edge, and the flow at the moment is greater than 0. Then you create a back edge, V to U, with its residual capacity equal to the amount of that flow. And for E equals UV, and its current flow less than its capacity, then create a forward edge Yeah, this was from U to V, so the back edge is V to U. Forward edge U to V with its residual capacity C prime E equal to whatever its original capacity was, minus its current flow. And that's the residual capacity. And then you find an ST directed path, if there is one, else you stop if there isn't. And with min residual capacity denoted as B, and then you modify the flow F prime E equals F of E plus B for a forward edge, edge E, and F prime E equals F of E minus B for a backward edge. Well, I need to actually be a little more careful about this one. So if the original edge E is UV, and the backward edge that we're talking about is VU. Okay. So this is, it's in the path. Oops, got to be more careful than that. Find an ST-directed path P, and then this is for E, for an edge E that's in P. So if E was a forward edge, then you just increase its, what you're assigning to it by B. But if the reverse of that is a backward edge, then you're going to decrease the flow on edge E by B. Okay? And then we just said iterate this. Well, and you just keep doing that. But to make this formally make sense, you had to assign f prime to f. Well, this is where all the real work is. It's in building the residual graph and then finding an augmenting path. P is called an augmenting path. And if that path exists, then you keep going. And again, I don't want to spend too much time reviewing, but I don't want people to be totally lost either. So we had this little example, 20, this is U, 10, T, 30, V, 20, 10. And if we started out with F being 10, 10, no, I think we started, sorry, our first F was like 20, 20, 20. Then the residual graph was S, this would be 20, you would have here a 20, because, no, sorry, a 10, and then that would be a 20, and this would be a 10, no, sorry, V, that's forward, and this is T, this is a back of 20, and this is a forward of 10. Is that right? That's the residual graph. Okay, and then we find an ST path. Here's one. Okay, and the minimum there, B is equal to 10. Okay, and this is just the example we did last time. I'm just trying to warm everybody up here. B equals 10, and then we use that path and the minimum value B to modify the flow. Okay, well, this was a forward, no, this is the path, sorry. This is a forward, okay? So it gets now, previously it had been a flow of 0, now it gets the flow of 10. It becomes a flow of 10. We're adding the B to 0. This one is a back edge, okay? So the flow here, which had previously been 20, now becomes 10. It's 20 minus 10, which becomes 10. Okay? And this edge is a forward edge, so the flow here, which had previously been 0, now becomes 10. And you can see that, again, we have a flow, and the flow value has increased. It had previously been 10, and now it's, what would it have been? Yeah, 20, I guess, and now it's 30. Okay, so that's the review of the algorithm. And then we had a claim or a theorem last time that I know I finished, although quickly, but I'm going to leave it, that f prime is a flow. Okay, so when you make this, when you make these changes, you do this augmentation, you actually create a flow and maintain a flow. And in order to verify that, you have to look at the definitions of a flow. You have to make sure that f prime, those assigned values on edges, are within 0 and the capacity of that edge. And then you also have to verify that you have conservation at each node, that the amount flowing in is equal to the amount flowing out, except at S and T. Okay, those are the two where you don't have conservation. And that's what we verified quickly last time. And I'll let you do that yourself. The details are in the book if you didn't absorb it from the last lecture. All right, so let's go on from there. Page 2, page 3. All right, next claim. if the capacities are integers, then the algorithm terminates. Well, sort of as a sub-claim before that, I should have perhaps claimed that the value of the flow f prime is strictly greater than the value of the flow f. Okay, so the value of f prime is greater than the value of the flow f. In fact, Vf prime is equal to Vf plus what? Plus what? B, yeah. So in fact, when you look up here at the proof that f prime was in fact a flow, you were seeing how the amount flowing into a node was changing, and we were still having conservation. The amount flowing in was equal to the amount flowing out, but it could in fact increase. I mean, along the path that that's found here. And for example, if you had a forward edge followed by another forward edge, this is a plus b and another plus b. So more is flowing in here, and then the same amount, additional amount is flowing out. And ultimately, when you get to, well, let's just look at it from the standpoint of S. There's an edge going out of S that's in P. What kind of an edge is this? Forward or backward? It's got to be a forward edge because there, in the original graph, there are no edges into S. Okay, so there can't be. So in the residual graph, when we're looking at an edge that goes out of S to some other node, that must in fact be a forward edge, one of the original edges, and therefore this is getting an increment of plus b. Okay, and this is our path goes from S to T. I should have emphasized that it never returns to S. So it's just a simple path that goes from S to T, and therefore the amount that's going out of S is increased by plus b compared to what it was previously. And similarly, we could do an analysis that shows the amount that comes into T is plus b. So we're seeing an increase here. Now, b is strictly positive. Okay? Because if we ever had a residual capacity of 0, in fact, those edges weren't put in there, right? If I look at the rules here, here we have a forward edge. The flow is strictly less than its capacity. Okay, so that was a forward edge that was put in there. And here we have a, no, sorry, this is a forward edge. And capacity minus its flow. I guess we could have had a 0 here. There's that. A 0. Well, okay. And there's no point in putting an edge in the residual graph that had a 0 capacity. So we'll just have edges that have non-zero capacity. And then we're always increasing flow by some amount, and therefore we're increasing. Now, how does this claim the algorithm terminates? Okay, so I want to use this fact to claim that this algorithm eventually does terminate. Yeah. Right.
There's only a finite amount of flow coming out of S, so if each iteration takes up some of that flow, then there must be a finite number of iterations.
Okay, so when you said there's only a finite flow, did you mean finite capacity?
Yes.
Okay, yeah, right. There's only a finite capacity coming out of S, for example. So if we just look at that, we certainly can see that the flow could never be more than the total of the capacities of the edges on the edges out of S. Similarly, although it's the same in this little example, we could make the same argument for the flow that goes into T. And we'll actually see in a little bit that this is true for every cut. Well, I haven't defined what that is yet. But at any rate, certainly when you look at all the edges that are out of S, that's a limit, a finite limit on the total flow. And if we're increasing by some non-zero amount, then what?
There is a point that we cannot further increase it.
Okay, I'm just trying to be difficult here because there's a subtle point. And what's the magic word here that I'm looking for?
Integer point? Integer.
Integers, yeah. So we assumed, did we? Oh yeah, capacities are integers. We assume that the capacities are integers, therefore B is in fact greater than or equal to 1, and therefore we're with a finite bound on the capacity of the edges out of S, we will eventually get stuck, or we can't increase anymore. Okay, yeah.
I'm not convinced that it doesn't terminate if the capacities are not integers.
Okay. I guess there are a couple of implied negatives there. So all I'm pointing out right now is that the only thing we've proven is that if the capacities are integers, then the algorithm terminates. I haven't said that if the capacities are not integers, then the algorithm doesn't terminate, although in fact it's true. That's why I'm being so careful, and it's subtle. It turns out that you can rig up examples where the capacities are irrational, whatever that would really mean, where this algorithm makes B is greater than 0, and in fact the maximum flow converges if you run this algorithm, but it doesn't converge to the maximum possible. So this algorithm actually has a weird degeneracy in the case that the capacities are irrational. Okay, we're not going to get into that because we're going to, well, first of all, when the capacities are integers, then everything is fine. And we're going to see another algorithm eventually that doesn't have that degeneracy, but it's just a interesting historical point. Does everybody see where we are with this? I mean, we've proven termination with integers, and you just should see the plausibility, or at least the possibility, that without integers, with irrationals, for example, the algorithm could make increase flow at each iteration, but by smaller and smaller amounts, so that it converges to something other than the maximum flow. And in fact, it doesn't ever terminate because it's just a convergence to some. It's one of those epsilon delta things you did when you were a freshman. Okay, but for integral capacities, we're fine, and don't everybody blurt out the answer, because I'm going to put the question, this occurred to me that a good question on the next homework would be to ask you what happens with rational capacities. Okay. All right. So we've got termination, and now I want to prove correctness. Oh, actually timing. Suppose the capacity here, capacity sums, let's say to C, just some number C, okay? Then we know that the flow increases by at least 1 in each iteration. So we know that there won't be more than C iterations. And how much time does it take to implement each iteration? If you look at this algorithm, if you look at this part of the algorithm, you have to build the residual graph from the existing flow even if you do it in a fairly straightforward manner without any smarts or cleverness, you can build the residual graph in time proportional to what it takes to look at every edge in the graph. So if there are m edges in the graph, you can build the residual graph in time order m. And then when you're looking for an ST-directed path in the residual graph, again, if you did a breadth-first search or some kind of simple search of the graph, you would not have to do anything more than look at all the edges. And so certainly the termination can be done in order m times c time. Okay. Well, in this class and in this whole area of analysis of algorithms, one of the critical distinctions is between algorithms that terminate in time that's bounded by a polynomial function of the input size, and algorithms that don't, algorithms that terminate in time that's more than a polynomial, let's say an exponential. What about this thing? Is this polynomial or exponential? I hear polynomial, exponential. What about don't care? No, I mean none of the above. It's what?
Do we consider capacities as integers, or
Yeah.
can it be kind of functions?
No, right now we're just talking about integers.
So it's polynomial.
Okay, it's polynomial. All right, well, the real answer is it depends on what C is. I mean, to do the full analysis, we'd have to ask ourselves, how big can C be as a function of the input size? So polynomial means growing in a time or number of operations which is bounded by a polynomial function of the size of the input. Size of the input here is the graph, which is m, number of edges, plus some representation of the capacities. Okay, we have to input what the actual capacities are. Okay, and the thing about numbers is that you can represent a number, let's say t, in log base 2t bits. So the size it takes to represent the number is just the logarithm of the value of the number. Okay? So the actual numbers can be exponentially larger than the space needed to represent them. And here we have a c in this time bound. C is actually the sum of the capacities of these edges. Okay? So it seems that the sum of the capacities of the edges could be exponentially larger than the space needed, the number of bits needed to represent those actual integers. Okay, so this is a long-winded way of saying that this is not considered a polynomial. It's not really obviously exponential either, because it really ultimately depends on C, and you'd have to go back and try to find examples, but they exist, where C grows exponentially larger than the space it takes to represent the graph, represent the networks. So this isn't quite what we are shooting for when we're looking for a polynomial time algorithm, and we will eventually construct a polynomial time algorithm. And it will also not have, well, if it's polynomial time, then it must terminate, and therefore it's not going to have this degeneracy about irrational capacities. Did you have a question? It looked like.
I just wanted to clarify that. So this is not polynomial. This is not considered polynomial because it's dependent upon the actual input.
Yeah, well, it's not considered polynomial because, well, everything depends on the input, but in this case it depends on the values of those numbers instead of just the amount of space it takes to represent them. Yeah, that's kind of a distinction I don't think we would make in an elementary algorithms class, but in a graduate course we want to be careful about those. All right, so now onward to correctness. Assuming we have integers, we want to prove correctness of the algorithm. So the algorithm terminates, we've proven that if they're integers, but does it terminate in the right, having found a maximum flow? Does the algorithm find a maximum flow? Okay, Well, in this business, it's very useful to look at a complementary object, or have a complementary consideration in addition to flow. And that's the concept of a cut. Or a cut is a partition of the nodes into, or maybe I should call it a bipartition. It just has two parts to it. A bipartition of the nodes into sets, let's say A and B. So partition means that no element is in both of those sets, and the union of those sets is the entire set of elements, so all the nodes. So the node set is equal to A union B, and the intersection is empty. Okay? And another definition, ST cut is a cut where S is in A, it's on the S side, and T is in B. Okay? And we usually just, something interesting about the human mind, I can't think about these things without doing that. Okay? Here's A and here's B. Okay, and so we've partitioned the nodes into two sets, which we can draw by those little clouds. Okay. Then the next critical definition before we actually prove something, I wanted to leave the algorithm up there and the example up there, so the board work is a little jumping around. Definition, the capacity of a cut AB is equal to the summation of CE, E out of A. Okay? So here's our little picture again. Here's A. Here's B. I have edges that cross. And we take here the summation of those capacities. And the reason I underlined this here is that we're completely ignoring any of the edges that go the other way. There may be edges that go from B to A. And one is tempted in this definition to subtract off the capacity of these edges that go the other way. But that's not what this definition says. The definition only counts and sums the capacities of the edges that go from A to B. Okay. All right, so now let's prove something. Let's see. I would like to keep this if I can. I wanted to keep that. Yeah, we need those definitions. I guess everybody has the Ford-Fulkerson algorithm blazed into their brains. So we'll erase that. Okay, so here's a theorem. Let F be any flow. We're talking always about flow from S to T. Flow. And AB be any ST cut. Then the value of that flow is equal to the summation flow E out of A minus summation FE E into A. Okay? And this, there's a notation for this that's a little more convenient. So this is defined, this triple means that the next step is just by definition and not actual any observation. This is F out of A minus F in of A. If you remember from last lecture, at the very beginning I put up some definitions on that board over there. And at some point in the lecture I said we're not even getting to the point where we're using those definitions. That would, this was the definitions here of we have a whole set of nodes, the summation of the flow values out of those nodes was defined as F out of A, and this was F in of A, and so on. So this is just a definition. This is the theorem, and this is just the use of that definition. So this is the generalization I said we would see about the, well, actually, I need to take it one more step. But what this says is that you can clock a flow by looking at any cut. Okay, you don't have to just look at the edges that come out of S or the edges that go into T. Any cut whatsoever, any ST cut whatsoever will tell you what the value of the flow is. So let's look at, let's say S and U together. Take that as A, and then take the other portion as B. Okay? So what do we have that goes across from A to B? We have this edge, which has a flow of 10. All right? We have this edge, which has a flow of 10. We have this edge, which has a flow of 10. That's 30. And how many do we have that go, how much flow is there from B to A? Well, in this case, it's 0. So this said flow out of A minus flow in of A. If we took that as our A, then we would have a flow of 0 going into A. Is there a more interesting example out in, what if I took, it's going to be really messy, but what if I took A equal S and V? Okay. Then flow in of A equals what? It's 10, because it's the flow along this edge is 10, and flow out of A, it's, remember, S and V, that's our A. Okay, so what's out of it is 20 plus another 20, that's 40, and 40 minus 10 is equal to 30. Okay, so that seems to work. It's always dangerous to do an example where I haven't worked it out ahead of time because, you know, just like in law, you're never supposed to, a lawyer is never supposed to ask a question in a courtroom where they don't already know the answer, what the answer will be. But anyway, this one worked out, so I got saved. So that's what this is saying, is that you can measure, and if you think of this physically, this makes sense too. I mean, if you have a river and you want to know how much is flowing along that river, and if you have a lot of tributaries to the river, you could either look at each one of those, or you could cross somewhere in the river where all the flow is going across that point, or go a little bit further downstream, or whatever. Any one of those places or systems of measurement should give you the same answer. And that's exactly what we're seeing here. That's what this theorem says. Now I have to prove it, which gives you a first look at how to how to analyze some of these things, these kinds of things. Okay. Well, we've already defined, so this is the proof. The only way we know presently, before we prove this, how to measure the flow is looking at what comes out of S. That was our definition of flow, or equivalently what goes into T. So this is what is out of S minus flow into S. How much is the flow into S? This is, I'm writing it so big it looks like a set, but this is the little, this is the, yeah, this is 0 because there are no edges that go into S. Anyway, so there's no flow into S. So this is just the flow out of S. Okay. And now I'm going to do something slightly tricky. That's equal to flow out of V, that's node V, minus the flow into V, where V is contained in set A. So the flow out of little node of the source node S is, and we know that S is contained in A. Recall that S is an A. This is an ST cut. But this says now I just take the summation over all the nodes that are in A, and it's the sum of what's out of that node minus what's in that node. Why is that right? Okay. This is sort of the tricky little step. Well, it's for the following reason. Because flow out of V is equal to flow in of V for all V in A except for S. Okay, by, not conservation, what was it called? What's that constraint called? Conservation and, well, anyway, the Kirchhoff law type law in flow. I guess it is called conservation, yeah. By the conservation requirement for flow, we know that the flow into any node has got to be equal to flow out of any node. That's for all nodes except for S and T. So in particular, that's for all nodes in A except for S, because T isn't in there anyway. So they all cancel out to 0 except for the flow out of S. So that's true. Now, why do we care? Page 5. Okay. So this is what we know about the flow value. It's equal to this thing. And now, if you draw one of those little pictures, here's A. We have 3 kinds of edges with respect to A. We have edges that go out of A into B. We have edges that go from B into A. And we have edges that are strictly inside of A. Okay? So let's make this a U to a V. All right? So if we're looking at this thing again, and you look at an edge that's strictly inside A, it's going to go from a node U to a node V. Actually, I shouldn't keep, let's call this a W. It goes from a U to a W. Now, the point is that this edge has some flow on it, and it goes out of U, so it's going to be contributing to an out somewhere in the sum. It's going to be the out when V is equal to U. Okay? But it's also in to some node that happens to be an A, namely W. And so it's going to be contributing in the sum to some in amount when V is equal to W. Okay? So whatever flow is on here is going to cancel out in this sum. All right? Then we have edge like this that goes from, let's make this U again, U to W, where W is in B. Okay? So in that case, we have a flow on this edge that goes out. It's going to contribute here, but the in portion of that flow is in W, and W is not in A, so that doesn't, the in part doesn't get contributed there. And then we have the flow from a node in B to a node in A, and so the out portion doesn't get counted, but the in portion does. All right, all that is sort of a long-winded way of saying that this is equal to F out of A minus F in of A. Okay, which you might have been be happy to believe anyway, just by distributing this sum without doing this case analysis. But I wanted to do it a little bit more formally. So our point is the flow value is the flow out of A minus the flow in of A across this ST cut A. Okay? That's what we've proven. And that's what we wanted to prove. Okay? That's a check mark. So what we wanted to prove was that you take any ST cut, call it AB, and if you look at the flow that's out of A and you subtract off the flow that's into A, that's the value of the flow. You've measured the flow across that cut. Okay, so there are some nice immediate corollaries to that. For example, now let's put the, I don't think I'm going to get to where I'm going to use this picture again in today's lecture, unfortunately, so I can erase it. So let's get some corollaries. Well, one of the corollaries, actually, this is kind of cheating. Maybe I did this. This is probably not, I shouldn't blame this on the book. I probably wrote this down in preparing this lecture. I have here as a corollary that the value of the flow is the amount that's flowing out of S. Okay? And I said that's a corollary because, well, out of S, we have an amount that's flowing out, but we don't have anything that's flowing in, and therefore this is just a special case of that. But now why is that cheating? Now that I think about it, why is that a totally illegitimate thing to call as a corollary? Yeah, we started there. We had that as an assumption. That was our definition. We defined the flow out as, the value of the flow is what was flowing out of S. Okay? And we said we justified that earlier by some earlier arguments or a definition. So, you know, I should not call this a corollary. I just say we certainly haven't violated that. In this conclusion did not violate this thing, which is where we started. I mean, had it violated that, we'd be really confused. Okay. But anyway, so this note that is consistent. All right. But a real corollary is the following. Let AB be any ST cut, then the value of a flow, and F is of any flow, and F is any flow, or any ST flow, then the value of that flow is less than or equal to the capacity of AB. And the capacity of AB, well, it's right there. That's the summation of E out of A. Well, where does this thing come from? What's the proof of this? Well, it's called a corollary, so it better come from this thing directly. The value of the flow we know is equal to the flow out of A minus the flow into A. Okay? Well, the flow out of A certainly is bounded by this amount. And here we're taking something negative, reducing it. So if we turn that to 0 or just ignore that part, then we get this, certainly. Okay? And this is defined to be that. All right? So this says that the capacity of any cut, now it would have been useful, I guess, to have this figure, but any cut whatsoever, ST cut, is a upper bound on the maximum flow you can have. So in particular, we had mentioned that the capacity of all the edges out of S was an upper bound, but that's just one particular cut. We take any particular ST cut, and that will bound what the maximum flow can be, because this is F is any flow. Okay? All right. So another corollary, which is this is the out of A. Is there a question? No. Another corollary, well, I'm afraid I have to erase this. If F is a flow and AB is an ST cut where VF equals CAB, then what? So if you have a flow in your hand and you can exhibit some ST cut where the value of that flow is equal to the capacity of that cut, then there are two conclusions that we can draw. Then VF is the maximum value of any flow, ST flow, and what? CAB is the minimum capacity of any ST cut. Okay? So that's if F is a flow and AB is a ST cut which has this equality, then we can draw this conclusion. Okay? Hopefully everybody can see this, or when you think about it at home, you'll see that these two things this must be true. I mean, any F has according to this, that the value of that flow is less than or equal to the capacity of any cut, and yet we have one in our hands now. It means that those two, here's flow, here's cut. Yeah. And if they're equal, this must be max, this must be min over the set of all flows and cuts. Okay. So I'm running out of time. I'm just going to throw up right now the theorem, and we'll prove it next time. That one of the theorems that makes this max flow so interesting and useful for any G, for any graph, even with irrationals, by the way, VF equals CAB for some F and AB. Another way of saying this is max flow equals min cut. So you take your network and you find the smallest possible cut. There is always a way of finding a flow, an ST flow, whose value is exactly equal to that. The Ford-Fulkerson algorithm doesn't find it in the case that we have irrationals. I've said that. It does find it in case of integers. We haven't finished proving that. We'll finish proving that next time. And as a consequence, we'll prove this theorem, which is a max-min theorem. Where have you seen a max-min theorem before? On your current homework, I think. Okay. So these max-min theorems come up all over the place, and this in turn turns out to be a special case of what's called duality theory in linear programming. So I'll see you next time.